Hi everyone, this is Sutirtha doing my doctoral research at Merit University. I would also like to mention the co-authors of this paper, Shyam Kishor working in Genpact, Bangalore, India, Shubham Patil studying at SVNIT India, and Dr. Joseph Timoney, my supervisor at Merit University. Today I will be presenting our paper, LeaderSTeM, a LSTM model for dynamic leader identification within musical streams. A music ensemble is a collaborative performance by musicians and singers. Music offers an unique abstract way for expression of human emotions and moods wherein the melodic harmony is achieved through pitch, rhythm, tempo, texture and other sonic qualities. The emerging area of robot musicianship focuses on the development of machine intelligence in terms of algorithms and cognitive models to capture the underlying principles of musical perception, composition, and performance. To explicitly perform, the key ingredients of a good symphony are synchronization and anticipation, which means understanding the beats and identifying and following the correct leader. One of the major characteristics of a musical performance is that musicians do not engage with rigidity. Rather than they play, move, and act as per they feel of the music. Further, the role of different musicians in an orchestra changes following a rhythm communicated in real time either through mutual nonverbal gestures or by a principal conductor. Thus, there is a smooth transition of the musicians between the role of leader and follower. Each musician is connected to every other musicians during the process indirectly or directly representing the whole system as an connected graph. The two essential features of the communication would be mainly auditory response and the nonverbal expressions. The auditory response helps the musician to understand the musical part. At the same time, the gesture boosts up the expression and the feeling in the performance. Over the years, the researcher had been studying both audio and nonverbal aspects together to decode the underlying physics of human synchronization and group performance where time plays an important role such as this kind of musical activity. However, in this paper, we tried to explore machine learning models and their potentials to understand and follow a dynamic leader who keep changing over the time of the performance using audio features only. This result would be especially useful in an analysis of scenario where there is no video or eye tracking or gestural data available, but only the audio data, which is often the case. To simulate an ensemble performance, in this experiment, we used a STEM dataset, the MSU DV18 dataset, which consists of total 150 complete music tracks. These are of distinct genres that contains mix of vocal, drums, bass, and other accompanied instruments. All the tracks are stereophonic as well as sampled at 44,100 Hz. As we can see on the left hand side top image, the dataset consists of a full mix track divided into 4 stems or individual instrument subtracks: the drum, bass, other accompaniment, and voice. We used PyAudio's Python library to capture live audio buffers and used Obio's beat tracking, pitch and amplitude functions to generate tempo, pitch, and volume from each audio buffers. We extracted this for each stems and the full mix track in real time with a window size of 1024 and a hop size of 512. From the table down below, we can see that we have 12 input features and one target output feature. We took a sample file and tried to visualize it. In the initial stage, the mixture follows the other accompanied instrument, and then it follows the drum, and lastly it follows the bass. Around the samples of 8,000 to 12,000, there is a significant change in tempo. Around 8,000, there is a significant lowering of tempo, and around 12,000, there is a significant increase in the tempo. So we can consider this file to be a good test case to check the maximum potential of the machine learning model which we developed called LeaderSTeM. In this experiment, we split our dataset into two halves, training and testing, with a ratio of 8:2. Then we find possible correlation in the set of features. We used principal component analysis or PCA and observed the cumulative value of the variance as shown in figure on the right hand side. It reaches 1 when all the features are included, so we had to use all the features to build our model. Initially, we explored the three different non-linear learning models. These are random forest, support vector machine or SVM, and long short-term memory or the LSTM. On evaluating these three machine learning models, we find that the two-layered LSTM performs much better than the other SVM and random forest. The metric we used for evaluation of the performance was mean squared error or MSE. After seeing the performance of a two-layered LSTM model very good, we expanded our search on 3-layered, 4-layer and 5-layer LSTM models to find the optimal and the best LeaderSTM model. To achieve this, we used the rate tuner for hypertuning. We set the learning rate from 0.001 to 0.1, the number of nodes in the hidden layer from 2 to 512, the number of hidden layers 3, 4 and 5. The activation function we used here was ReLU. For each model we ran 10 epochs and the batch size was 32. Finally, we get the best model, which had the learning rate of 0.82 and the unit 1, 2, 3 was 445, 481 and 37 respectively, which gave a mean squared error of 245. Lastly, when we use the LSTM model for prediction, we see the first part follows the vocal, which was unlikely with the test dataset marked with red color on the slide. The second part follows the drum and the others accompaniment, which partially matches with the output dataset. And the last part, it follows the bass similar to the test dataset. So from this model, we can understand LSTM models like LeaderSTeM can be used to understand and identify the leader correctly. The model was able to understand the time-varying leadership during the performance and also was able to follow the leader correctly from the pitch, volume and tempo features. It was also able to adapt sudden tempo changes like in the middle of the song when the BPM of the song suddenly drops down and again rises up. Thus, this work shows us how to use the STEM dataset for simulating an ensemble performance. The LeaderSTEM model can be useful for robot-human interaction scenarios that requires a real-time BPM analysis to understand the leader. For future work, we will try to expand the search space, also incorporate visual gaze and body sway along with audio features to detect appropriate leader. Thank you very much.